Here we're going to get into trends of properties that exist on the periodic table, that there are certain patterns. Just like there's patterns to seasons, which is the analogy they're trying to draw there, there are patterns to the properties on the periodic table. There are lots of patterns on the periodic table. We're only going to look at a handful of them in this one here, but these patterns repeat as we keep going across the periodic table. As I just mentioned, when it comes to electron arrangement, the last number of things that are in a column together matches, and it matches their group number. And so you can see here the examples that they've given you, and they all end in the same thing. That's a pattern on the periodic table. Here's the rest of them if you want further proof of it. What that means then is that the outermost electrons, what's called the valence electrons, the electrons that are on that last energy level out there, match. Everything in a group, their group number gives you the number of valence electrons, as long as we're talking the Roman numeral group number. It is the one advantage of the Roman numeral system. Beyond that, I think it's easier just to count the columns and skip the transition metals in the middle, and then that roughly gives you the Roman numeral number, and it's just simpler. But everything in the first column, the first group of the periodic table, has one valence electron. Everything in the last column has 8 valence electrons, again, as I mentioned earlier, with the exception of helium. But everything in the halogen column has 7 valence electrons. It's why these elements end up behaving similar to one another, because they have the same number of valence electrons, which then affects how reactive they are. They're very similar in how they behave. Anyway, correct number of valence electrons then is just figuring out your columns here. So strontium's in the second column, so 2 valence electrons. Argon is in the last column, so 8 valence electrons. And silicon is in the 14th column, so 4 valence electrons. From there, as I mentioned already, we can go from Bohr models down to Lewis models. With Lewis models, we drop the rings, we stop drawing the rings, and we only draw the valence electrons. And so, for example, here where aluminum has 2, 8, 3 for its electron arrangement, we only draw 3 dots around it. And so the normal way to do this, and the next slide is going to contradict me on this, but I don't care. Trust me here. The normal way to do this is to go around and put a dot in each location. Once you've done that, then start pairing them. This will help you later on when we get to bonding if you do it that way. Or as actually drawing the dots: 1, 2, 3, 4, 5, 6, 7, 8. They tend to be drawn on the sides like that, above, below, and on either side. The standard that I have seen starts at the top and goes clockwise around. Not that you have to do that. This one here shows you all the different ways you can draw magnesium. I will point out that right angle tends to be better than across. Across is acceptable, but these other right angles, you would be starting somewhere else or possibly going a different direction. You'll notice if we look at them arranged on the periodic table, everything here has 1 valence electron, 2, 3, 4, 5, 6, 7, and 8, and they even mention here that helium is an exception to that. Again, you can just go back and look at it for a couple of these here, but I'm going to work them out. Chlorine has 17 valence electrons. It's in the 7th column, or you could do its electron arrangement 2, 8, 7. Any one of those 3 can get you that it has 7 valence electrons. So chlorine, we draw its symbol. I tend to do cursive L's to make it distinct from an I or a number 1. I should say cursive lowercase. And then we'd put 7 dots there. Selenium has 6 valence electrons. It's in the same column as oxygen. It's column 16. Drop that 1 and you've got 6. Or you can try the electron arrangement. Again, that's getting into those higher ones that we're not really going to do. Or you can look at its Roman numeral group number also. Potassium is in the first column, so 1 valence electron. And it's also one of the ones where the name doesn't match the symbol. Next here we have atomic size, and size is usually measured as the radius of it. There are different ways of measuring the radius, and a lot of times they're calculated and not actually measured, and so there's different ways to do that. There's no reason why we couldn't do the diameter, but radius is what tends to be done, and it's the distance between the nucleus and the valence electrons. And it turns out that as you go down the periodic table, it gets bigger. As you go across the periodic table, it gets smaller. Or the other way that you'll see this described sometimes is instead of describing it for both directions, you'll describe it in one direction, that we go bigger down and to the left. And from there, if you're going up, okay, smaller. And you're only ever going to be asked questions about ones that are above and below one another, side by side from one another, or ones that are on that diagonal. The opposite diagonal, if we were to do that here, this one here, well, you're getting smaller this way as you go across, but you're getting bigger as you go down. And they're kind of in a tug of war with one another, and I'm not going to ask you to predict which one it is. Now, I will point out that this one here, even though they show the atom size here, they're actually showing another trend that we'll get to here in a bit, something called ionization energy. It turns out that ionization energy has some similarities to the size. It's related to size, it's why. But as we go across, it gets smaller. And that sounds weird, because as we go from, if we just take hydrogen and helium, hydrogen has 1 proton, 1 electron, and normally has 0 neutrons. There are different isotopes of it that actually have 1 and 2 naturally occurring. Helium has 2 protons, 2 electrons, and it turns out usually 2 neutrons. So we're adding more pieces. Why does it get smaller? Well, it has to do with where those pieces are going. With hydrogen, you have 1 proton in the center, and you've got 1 electron, almost a good circle, orbiting around it. With helium, on the other hand, you have 2 protons down here in the center. I'm going to leave out the neutrons, and those 2 protons each pull on each electron. The electrons aren't together, and so on hydrogen, the 1 proton pulls on the 1 electron. On helium, both protons pull on that electron. They pull it in closer, and then they both pull on the other electron and pull it in closer. It's not like each electron gets its own proton. No, those protons are all together in the nucleus, and so then as you go across the periodic table, the atoms get smaller with the electrons out here. Well, as you go down, you're adding those energy levels. So here we have 1 ring, here we have 2 rings, here we have 3 rings. And so then they're getting bigger as you go down, smaller as you go across. Unfortunately, you do need to know these patterns. You're allowed the note card. Feel free to put them on there. It's up to you whether you do this kind of pattern where you're talking about whether it's increasing, decreasing each direction, or whether you do the one where I combine them. Like as you go this direction, they're getting bigger, or you could do the opposite one. Even as you go this direction, they're getting smaller. So that's up to you, but you do need to know these patterns, unfortunately. I will say most of these patterns I haven't memorized. I think through. I literally think through that atom size and it pulling in. Now, I've thought through it often enough as a teacher that I've eventually memorized it. But as a student, maybe I crammed for the test and learned them. To be honest, I probably wasn't a good chemistry student, and I probably just guessed at them. And then now that I have to teach it, I know it, and now I already know how to reason through it, and I've reasoned through it often enough that now I've accidentally ended up memorizing it. But I really do encourage students to think through it, because some of these are similar trends or opposite trends, and they start to get confused very easily. Anyway, this one here just asks us to list the largest in each pair. Yes, you could use this one over here, but as we go down, it gets bigger, so potassium is below lithium. As we go across, we get smaller, so then silicon is bigger than sulfur. And here we've got potassium and bromine. So those are here. That is in the opposite direction of this one here, so potassium is bigger. So next, we have something called ionization energy, and that is the energy needed to remove one of the outermost electrons, one of the valence electrons. And it is the energy needed to make it an ion. So sodium here that's neutral would be an atom. Sodium here that has a charge would be an ion. And then, of course, you get these electrons floating around out there as well. Well, if you think about it, the smaller the atom is, the closer those electrons are going to be to a more highly charged nucleus, the harder it's going to be to pull an electron away. The 9 protons here in fluorine are going to hold on to their electrons more strongly than the 3 protons in lithium. And those 9 protons have also pulled those electrons in closer. And so now you're having to fight against, it's a tug of war of you versus 9 protons out here at fluorine, but it's a tug of war between you and 3 protons for lithium. So of course it's going to be easier to remove an electron here. So as you go across, the ionization energy increases. It gets harder to remove the electron. It goes up. Now, as those electrons get further and further away from the center, because the atoms are getting bigger as we go down, then it's easier to remove the electron because the nucleus is way down there in the center and those electrons are way out above, and so then it's harder to grab them and pull them in. So the ionization energy decreases or goes down as you go down the periodic table. And so that pattern is related to the size and to the charge of the nucleus. So from here, we're just asked higher ionization energy. It's the same set. I will say, if you're on the original slides, I'm pretty sure that they have the wrong question for C, but then if you flip to the next slide that has the answers, they have the correct answers there. Anyway, ionization energy, it's easier to ionize as we go down. The ionization energy decreases, so the higher ionization is going to be lithium. It's harder to ionize as you go across, so the higher ionization energy is going to be sulfur. And calcium bromine here, it's harder as you go across, so bromine is going to have the higher one. This brings us to a trend that I personally wasn't taught as a student, though I've seen it plenty of times since, and I don't know that I like. I always thought of this one in terms of reactivity, and that we could compare metals and nonmetals separately from one another and essentially have a pattern for reactivity with metals and a pattern for reactivity with nonmetals. But another way that is described is metallic character. How metal-like are they? And so it turns out that the you are more metal-like if you are on the metal side, and you are less metal-like if you're on the non-metal side. Big surprise there. Well, it's not just a left-right pattern, it's also an up-down pattern. It means that the most metal-like metal is cesium, and the least metal-like non-metal is fluorine, or really the noble gases probably fit in there. I'm used to thinking about it in terms of reactivity, and the noble gases don't react, and so I think of fluorine is why my mind jumps there. But the metallic character decreases going across, and it increases going down the periodic table, or again combining them, increasing metallic character this way. Another way that you can learn these trends as well, it just popped into mind because of the way that I remember fluorine there, is you can memorize the extreme cases and then derive, that is, rethink through, come up with the pattern from there. I did that for reactivity. To some extent, I've done that for ionization energy. But cesium and fluorine, if you can remember their sizes, their metallic character, their ionization energies, then it's easier to figure that out. So getting into metallic character, both lithium and potassium are metals, but potassium is further down to the left, so potassium is more metallic-like. Sulfur, silicon, neither one of those are metals, but silicon is in that metalloids, kind of metal-like, and again, it's to the left. Calcium bromine, it's the same thing here. We have a non-metal and a metal. Of course, the metal is going to be more metallic than the non-metal. So there you have it. Here are those trends in the periodic table that we just went through. There are all sorts of other trends. If you're live with me, we'll do a lab where we actually graph these and some other trends. We'll look at some patterns in boiling point and melting point. We'll look at patterns in density. We'll look at patterns in something called electron affinity. And we'll also look at other ionization energies. This ionization energy here is technically the first ionization energy. There are also second ionization energies, third ionization energies, etc. And that's the amount of energy it takes to remove another electron. Not how many it takes to remove 2 for the second ionization energy, but after you've done the first ionization energy, how much does it take to remove the next one? So if you're live with me, again, we'll take a look at some of those. But anyway, those are the basic ones that you need to know. Anyway, here we're given 3 elements. It's just asked a handful of questions about them. So which is the largest atom? That is going to be lithium, because all 3 of those are in the same row of the periodic table. Highest ionization energy, that's going to be fluorine. It actually has the highest of the ionization energies. ignoring the noble gases again. It belongs in group 15 or group 5A. Well, that one's going to have 5 valence electrons, or as nitrogen. Most metallic character, well, that's going to be our only metal on there. Anyway, that finishes up my favorite thing. Unfortunately, we don't get to spend longer on this, but that is atoms, elements in the periodic table. As usual, there's a concept map here if you want to take a moment and read it. It's also in your textbook. And of course, if you have any questions, be sure that you let me know.